All right, so next we're going back to surfaces and observations, I think, and Carey Legett is going to talk about characterizing the optical effects of nanophase absorbers and mineral powders.
All right, well, thanks everyone for being here today and listening to this. Unfortunately for you, I don't have any really cool flown hardware experiments or fun videos to watch. We're at the stage in this experiment right now where we're generating way more questions than we're generating any kind of answers. So this is really just kind of an update on some stuff that I've done previously. So our main motivation for this study is to start characterizing the optical and spectral effects of these nanophase absorbers that are formed through the space weathering process. It's really poorly understood, the optical characteristics of these nanophase particles. We're talking some things down on 5 nanometer level. And by that I mean that the remote observations in the models are not yet matching up. We can't really get a good handle on matching what we see. So what we've started out with doing, trying to approach this problem from kind of a basic optics standpoint, was to get a scattering matrix, a strongly scattering matrix. For us, we use silica aerogel to see what happens when you have something that's very small that's scattering the light at all these wavelengths. A transparent matrix that we can embed things in, and then a strong absorber, which for us is amorphous carbon black, because nanophase metallic iron is impossible to use in a normal laboratory setting. So when we talk about scattering, we kind of have to think in terms of 3 different types of behaviors: geometric, mean, and Rayleigh scattering. The main control on which one of these 3 regimes we're in is the particle size to wavelength ratio. To describe this, we use the size parameter, which is 2 pi the radius of the particle over the wavelength in question. And when you're much smaller than 1, you're in Rayleigh scattering, something like the atmosphere of the Earth. When you're about 1, you're kind of in the me range, which is something like you would expect a cloud to scatter. And then when you're much larger than 1, you're in kind of your intuitive optics, mirrors and lenses, refracting, that kind of stuff. For what we're doing, we're almost entirely in the Rayleigh and me ranges. So one thing to remember is that what is going to cause scattering of light? So the kind of classical scenario is that you have some sort of particle embedded in a medium, and when light interacts with that, it is scattered in some way, shape, or form. But conversely, if you have a void in a medium, that void will also act as a scattering center, which is very important to us because we're using aerogel. If you're not familiar with what aerogel is, it is a kind of nano framework of very thin filaments of silica that are surrounding a bunch of voids. It has a density very close to that of air, and it is an extremely good thermal insulator. This is a TEM image to get, kind of give you a scale of a 2-dimensional projection of an aerogel network. And you can see that we have some of the largest holes in here about 20 nanometers, and some of the smaller ones are probably down in the 1 to 5 nanometer range. So this is right about the sizes we're talking about. This is a picture I actually took at the Juno launch. That's me holding a chunk of aerogel, and there's a reason that they call this stuff solid smoke. That looks an awful lot like a little bit of a cloud of some sort. You're off viewing axis from the light that's passing through it, and so you're seeing white and blue coming off. When you hold it up to the light and look at the transmitted light, you get the longer wavelength red light that's being transmitted, just like the atmosphere at sunset. Our samples are a ground up powder of this stuff that we then grind to various powder size, or various macroparticle sizes. So we have little chunks of these scatterers, and then we mix carbon into it. So this is in the visible and near-infrared. We go from 350 nanometer wavelength on the left over to 2.5 microns on the right. And the features that you see here, the strong absorption features, are due to adsorbed water for the one at about 1400 and the one about 1900, and then this is a silicon feature over here. These really small guys, just to the left of the 1400 nanometer water feature, are probably leftover surface methyl groups from the manufacturing process of the aerogel that just didn't completely bake off when we were preparing this sample. So the only difference in the 5 samples that I have up here is the particle size that we've sieved to. So we go from the smallest size fraction, which is our sub 32 micron fraction at the top. And then these three in the middle behave fairly nicely, where it's coarser at the bottom, finer at the top, which is what you would expect with most powders. And we kind of have this outlier at 90 to 125 microns. No real particularly good reason for that. We're not really sure why it's shown up that way a couple of times, but that's one area of future investigation. So the takeaway here is that just like you would expect with a terrestrial material, the aerogel seems to be brighter the smaller the macro particle size gets. The other thing to notice is that all of these have what we would call a blue slope, which means that intensity of the reflected light decreases as wavelength increases. This is very characteristic of an off-axis viewing geometry of a Rayleigh scatterer, just like I showed you with the big sample of aerogel in the picture from my hand. So there's no real surprise there. However, when we take those same samples under certain other viewing conditions, sometimes we see this round out, and we have not yet tracked down what this is due to, this round out at short wavelengths. So this is and this is not mislabeled, that is actually sub 30 micron, and this one is sub 32. It shouldn't be any different, but this is the clean aerogel sample. And then the one at the bottom down here, we have mixed 0.1 weight% amorphous carbon black into the sample. And so we dropped the maximum albedo from something of around 0.85 down into the 0.47 range at best. So 0.1 weight% carbon, and you're having the reflectance. The other thing is that, remember that this carbon that we added is 400 nanometer diameter particles. And we see this shift in concavity of the spectrum here, and we're starting to see what we might call a Rayleigh peak down at the short wavelengths. So even though the carbon is absorbing, we think of it kind of primarily as an absorber, we also see it acting as a strong Rayleigh scatterer because it's a smaller overall particle size. Moving on to our transparent matrix stuff, we chose halite because this should be in quotes. There are no spectral features in the mid-infrared or visible near-infrared. That's assuming that you can get a really truly pure halite and that you don't add anything to it in the processing or handling of it in the laboratory, which we have not yet figured out how to do, including the purchasing the pure stuff. So this also has an extremely low K value in the visible and near-infrared, so any absorption should be due to something that we've added to it. And sure enough, we get our very pure halite here, and it's got a reflectance of 0.9 to 0.95. You add 0.1 weight% carbon, you cut it in half, more or less. 0.2 drops it down to about 0.25. 1 weight% carbon is a little bit lower. 2 weight% carbon, and then this is just pure carbon that we stuck underneath there. So this is not at all surprising. You would expect the more absorbers to follow some sort of logarithmic law and kind of asymptotically approaching the end member down here at the bottom. If I normalize all of these so that you can see slight variations in the absorption features and slopes, so all I did was stack them on top of each other now. We go from the pure halite, which is the red, and you can kind of ignore these guys. These features up here are probably due to a bad calibration to our spectralon standard. The red line, which is pure halite, has a very sharp fall off as we get out towards blue into the UV. When we add that, I should mention that this halite has been ground to the sub 1 micron fraction. So there's not a huge difference in size in this. When you add that 400 nanometer carbon, we once again see that upturn into the Rayleigh peak here. The fall off right at the edge on all of these is due to approaching the bandpass filter on our spectrometer. So that there's kind of a trade-off, and we're losing information at the edges there. But we don't really see quite the same thing in the pure carbon, which is the white line. There's maybe a little bit of a rise, and we do have this kind of overall blue slope, whereas the others have a red slope to them, but we don't really see that. I don't yet have a good explanation for why that's the case, but I have something that might have to do with it I'll get to in just a second here. Flipping now into the mid-infrared, these are the same samples I just showed you. We've got pure halite at the bottom here, and then we go up to 0.1 weight% carbon in the blue. What do we have? 0.5 weight% in the orange, 1 weight% in the white, and then the red. Yellow is 2, carbon is red. Kind of cool here. If you see this is the emissivity of one line. that those cross over there. And we believe that this is an accurate measurement. And what I mean by that is this is a better these samples are better black bodies than our black body calibration target at these wavelengths. Another interesting thing is that we see that the carbon is falling off steadily as wavelength gets longer out here. And then the halide approaches an emissivity maximum right at about 325 or so wave numbers. And the result is that even though you have this, what you consider strong absorber, high emissivity, I mean, they use carbon black and high emissivity paint. That's one of the main pigments they use for it. The halide is actually a stronger absorber out at these wavelengths, and it completely dominates this region of the spectrum. Let me flip to this one. I just got rid of the pure halide. Otherwise, this is the same so that we can kind of see some variations in scale here. One thing that we're very interested in that I don't yet have an explanation for, but I've got a kind of a blind guess, speculation, is that you see this ripple in the carbon halide data, and it shows up in all 4 of those samples up there. And you don't really see the same thing in this lower sample. That's something we're going to try to model and see if we can get back to, but it could potentially be very interesting. So if you remember back when I was talking about the aerogel and halide, and we kind of have some weird behavior, we're hoping that we can model this. We have not yet gotten the models to cooperate, and by that I mean they won't run. If we have a strong absorber and we shine some light on it, we would expect that the top layer of the sample, these packed particles, is all that's interacting with the system. That any reflections that you get off the surface are coming from that upper layer, maybe 1 or 2 particles deep, maybe a little bit more, but not much. You're not penetrating deeply into the sample. If you replace that strongly absorbing matrix with a transparent matrix like halide, all of a sudden when you shine your light on it, you get a bunch of scattering down and into your sample. This multiple scattering allows you to interact with many more particles, and for certain light paths, it decreases the probability of a given ray path making it back out of the sample. So if we can find a good scenario to match this up with, where this stuff is sufficiently transparent and the particle sizes work out, this may actually have a higher emissivity and lower reflectance than the all absorber case. You can get some weird things happening here, and that will have to be a future update because as I said, do not yet have models to show on this. So for now, our conclusions are that very small amount of absorbers have a significant darkening contrast reducing effect. That's not a surprise. What was kind of a surprise going into this was that we actually have to account for this Rayleigh scattering. We're heavily focused on understanding Mie scattering because it's not something that we can easily model. But the Rayleigh effects are dominant at shorter wavelengths. In future, we have to get the computer models going. And we're going to get some additional size fractions on all of the halide and aerogel and carbon and everything to see if we can see this transition in behavior occur, see if we can find what size it is, or really what size, particle size to wavelength ratio it is, where we start seeing these effects show up. And then we're going to do some 2- and 3-component mixtures with kind of real-world minerals that we would expect to observe on planetary surfaces and see if we can match that to some real observations. So I'd like to thank my advisor and my group, and if there's time, I'll take any questions.
Thank you. All right, do we have any quick questions? Yvonne Pendleton?
Okay, wonderful talk. Thank you very much. I really enjoyed that.
Thank you.
I have two thoughts. One is a question about how did you get those little tiny aerogel fragments that you showed, like the white powdery stuff? Because when you touch aerogel, it just collapses into almost nothing in your hand. How did you physically do that?
So we actually bought it in that form. Cabot Corporation sells aerogel powders that are primarily used for industrial additives to paints and things, or dry powder flow enhancers. So we bought some that was nominally 700 nanometer to quarter. No, wait, not 700. 700 micron to quarter millimeter. 700 to 250.
Okay, I didn't even know that was possible. That's cool.
You can grind it without collapsing it. We actually did BET analysis
You can.
to prove that. Yeah.
Oh, okay. And then the other thing is in your diagram where you show the voids, how you have scattering off the voids.
Yes.
I know it was probably just simplistic, but you must mean that it goes all the way down, hits another particle and goes out? What
So
is
every time it
scattering?
crosses a particle-void interface, there is some scattering that occurs. And additionally, anytime it's traveling through any of these mediums, some level of absorption is occurring if it's not a vacuum. So every time that you leave or enter a particle, you're scattering. Anytime you hit an inclusion in a particle, you're scattering. And then, so really this was to show that if I could really delete all of the blue spheres here and replace it with a blue rectangle and kind of have the same idea where we have a very, very transparent thing that's not absorbing, that's allowing light deeply into the sample, not absorbing strongly. As it's scattering off light in different directions, that kind of incident beam is losing intensity and is less likely to hit something and bounce back out the deeper it gets into the sample. It's a very, very simplistic kind of multiple scattering model.
Great, thanks. We can